Let's begin with a metaphor. Imagine a thunderstorm raging inside the brain, not made of rain and lightning, but of molecules. These molecules are called cytokines, and while they are a normal part of the immune system, in excess they become destructive. When produced in overwhelming amounts, they can trigger a physiological phenomenon known as a cytokine storm, an inflammatory cascade so intense it can lead to organ failure in the body. But what happens when the storm targets not your lungs or liver, but your mind? In today's episode, we explore how these storms don't just occur in infectious disease. In recent decades, scientists have observed similar inflammatory signatures in people suffering from depression, bipolar disorder, schizophrenia, and PTSD. Cytokines, once thought to only respond to infections, are now seen as messengers that can fundamentally alter brain chemistry, cognition, and emotional regulation. In short, mental illness might not just be a chemical imbalance, it might be an inflammatory disorder, one where the immune system becomes the aggressor. To understand the storm, we need to understand its components. Cytokines are signaling proteins released by immune cells. They coordinate responses, recruiting other cells, inducing fever, promoting healing, or sometimes triggering cell death. They come in many types: interleukins like IL-6 and IL-1B, tumor necrosis factors like TNF-alpha, and interferons. Each has a unique role in immune defense. But under certain conditions, such as severe infections, autoimmune disorders, or intense physiological stress, this signaling system becomes hyperactive. The immune system starts producing cytokines in a positive feedback loop, meaning the more cytokines released, the more immune cells are activated to release even more. This is the cytokine storm, an uncontrolled inflammatory event where the immune system loses its internal brakes. In COVID-19, this storm often led to lung damage and death, but in the brain it can lead to something subtler, but equally damaging: neuroinflammation. Interestingly, psychiatric flare-ups like depressive episodes or psychotic breaks are now being investigated as immune events, where cytokine levels rise dramatically independent of infection. This challenges decades of dogma in psychiatry and neuroscience. So how do peripheral immune molecules affect the brain? Normally, the blood-brain barrier, BBB, tightly regulates what enters the brain. It's like airport security, very few things get through. However, systemic inflammation can loosen the tight junctions of the BBB, making it permeable to cytokines and even immune cells. Cytokines like IL-6, TNF-alpha, and IL-1B can either cross this barrier or signal through the vagus nerve to activate microglia, the brain's immune cells. When microglia become overactivated, they release neurotoxic molecules like nitric oxide, which interfere with neurotransmitter synthesis and damage neurons. Here's what we know so far. Serotonin synthesis drops because inflammation shunts tryptophan metabolism away from serotonin and toward kynurenine, a neurotoxin. Dopamine signaling becomes erratic, contributing to anhedonia, reducing motivation and psychotic features. Glutamate excitotoxicity occurs when astrocytes fail to clear excess glutamate, leading to neuron damage. And on top of this, inflammation reduces BDNF, brain-derived neurotrophic factor, a key protein for neurogenesis and synaptic plasticity. The result: poor memory, emotional dysregulation, and a diminished capacity for cognitive resilience. It's no exaggeration to say that cytokines can literally reprogram the brain, altering mood, cognition, sleep, and behavior. Let's zoom in on real-world flare-ups. In major depressive disorder, especially treatment-resistant cases, elevated IL-6 and CRP levels are often seen. Longitudinal studies have shown that high baseline CRP levels predict worse treatment outcomes, and even the likelihood of relapse after remission. It's not just correlation, this is a biological predictor. In bipolar disorder, inflammatory cytokines surge during manic episodes. IL-2 and IL-6 levels spike during mania and normalize during euthmic periods. Some researchers now hypothesize that mood instability itself may reflect underlying immune dysregulation. In schizophrenia, patients with higher TNF-alpha levels exhibit more severe cognitive symptoms and poorer outcomes. Microglial activation, measured via PET scans, correlates with gray matter loss in the prefrontal cortex. And here's a key point: these markers fluctuate dynamically with symptom changes. That means immune dysregulation isn't just a static trait, it's a state-based phenomenon, rising and falling with psychological distress. We're entering a new era of psychiatry, biomarker-based diagnosis. Until now, mental illness was diagnosed like it was in the 1800s, through interviews, checklists, and subjective observations, but immuno-psychiatry aims to change that. Today we can measure CRP, IL-6, TNF-alpha, IL-gamma, and even neoportin in blood or cerebrospinal fluid to track neuroinflammation. When elevated, these markers not only confirm systemic inflammation, but may predict treatment response. Patients with high CRP respond poorly to SSRIs, but may benefit from dopamine-targeting drugs or anti-inflammatories. Trials of celecoxib, an anti-inflammatory NSAID, shows enhanced antidepressant effects when added to SSRIs in patients with elevated IL-6. Experimental biologics like monoclonal antibodies against TNF-alpha are being explored for use in severe depression and schizophrenia. Moreover, neuroimaging combined with biomarkers is helping classify mental illness into biotypes. One group may show low inflammation and dopamine dysfunction. Another may show high inflammation and cognitive impairment. The future is personalized, data-driven psychiatric care. So what can we do to regulate the immune system beyond pharmaceuticals? This is where lifestyle psychiatry meets immunology. Chronic inflammation is not just triggered by pathogens. It's often sustained by modern life, poor sleep, ultra-processed foods, psychological stress, physical inactivity, and disrupted circadian rhythms. But this also means that we can intervene holistically. Exercise. Moderate aerobic activity reduces TNF-alpha and raises anti-inflammatory cytokines like IL-10. It also boosts BDNF and endocannabinoids. Omega-3 fatty acids, especially EPA, have shown efficiency in reducing depressive symptoms. They decrease prostaglandin production, a major driver of inflammation. Mindfulness and CBT reduce IL-6 and normalize HPA axis dysfunction. Sleep. Disrupted sleep increases IL-6 the very next day. Good sleep architecture is one of the most potent anti-inflammatory tools available. Gut-brain axis. A healthy microbiome maintains immune tolerance. Diets rich in fiber, polyphenols, and fermented foods reduce systemic inflammation via short-chain fatty acids. These aren't just wellness tips. They are clinical interventions that can shift the cytokine balance from destructive to restorative. Let's end where we began, the storm. We often think of mental illness as a chemical problem. Too little serotonin, too much dopamine, not enough GABA. But this framework is incomplete. Today we've seen that immune dysregulation may be the upstream issue. Cytokines can cross into the brain or be made by brain-resident cells, disrupt every major neurotransmitter system, shrink critical areas like the hippocampus, suppress neurogenesis and plasticity, and amplify emotional reactivity, hopelessness, and cognitive fog. But they can also signal healing when balanced. The future of mental health might lie in detecting these shifts early, treating them biologically, and empowering patients with tools to bring their systems back into equilibrium. Because sometimes the most dangerous storm is the one you can't see on the surface.